So let's start with looking at the differences between heat and temperature. Heat is a transfer or a flow of thermal energy from one object to another, or the flow can be from a system to its surroundings or from the surroundings into the system as well. The flow of the thermal energy starts from places or objects with a higher temperature, and the heat moves to places of lower temperature. Heat is measured in joules. So heat here is your quantity that we could measure, and the unit that it is measured in is joules. So let's take a look at these three scenarios. We have heat being moved from one object to another. So suppose we had one object here. So that's my object 1. And I have another object that's touching that object. That's 2. And this one here is hot. And this one here is colder. What we are saying is that the heat or the thermal energy is going to move from the hot object to the colder object. So it will move that way. The heat will move that way, from the hot to the cold. And this is when we have two bodies. Okay, one object to another. The second scenario is from a system to its surroundings. So suppose we had a system here, maybe a hot motor or a hot cup of tea, and this is hot. And then we have the surroundings, and the surroundings is your atmosphere, the air around in your room, right? So your surroundings. And this here is colder than your system or your object. The flow of the thermal energy or the heat will move from the hot object to the colder room. Alright, so it will move outwards from the hot to areas that is colder. The third scenario is when we have heat moving from the surroundings into the system. So for example, we have a block of ice sitting on your counter on a table, and the ice is cold, and your surroundings is actually hotter, right? So hot air in your surroundings. The direction that the heat would move would be from the hot air into the system. Alright, so from your surroundings into the system. And what will happen here? Your ice will start to melt. Okay, so these are three scenarios. From one body to a next, one object to a next, from a system or body to the surroundings, and or from the surroundings to a system. Of course, the most important thing is it moves from a higher temperature to a lower temperature. Okay? Now, when heat energy is absorbed by an object, for example, in example 3 here, it makes it hotter. And when it is lost by an object, it leaves it colder. For example, when a block of ice is placed on a kitchen counter, it absorbs the heat energy from its surroundings and melts. Right? That's what we talk about here. And when the water is placed in the freezer, it loses energy to the surroundings in the freezer and becomes ice. So you could draw a little illustration. You have your table, and then you have your block of ice on your table, and you draw your heat from the surroundings moving into the block of ice. So heat here is being absorbed by the ice. Okay, your surroundings here is hotter, and then your ice is going to absorb that heat and start to melt. That's the scenario here. And then the second scenario here is when the water is placed in the freezer. So you have your freezer, and you fill your ice tray with water. What is happening here is that heat would be lost. It will lose heat to the surroundings in the freezer, and the water will turn to ice. Okay, so the heat will come out of the water. Now, when we use words such as hot and cold, warm, tepid, or cool, it tells us about the hotness or the temperature of an object. However, these words are not precise, since what may be warm to you might be cold for another person. When we need to be exact about the temperature of an object, we use instruments to measure temperature, with graduations called degrees. A little later on in the lesson, we will talk about measuring temperature and the instruments we use to measure temperature, and we will look at the graduations and the units of temperature. An example of this here is having a fever. So you have a fever, but you feel cold and you're shivering, but at the same time your skin feels warm. You go to the doctor. To confirm that you have a fever, the doctor will use a thermometer to check your temperature, and this will accurately tell us if you have a fever or not according to your temperature that the doctor measured. So the words such as cold and warm and hot are not precise words that we want to use to describe heat. Now, heat and temperature are not the same, so you need to remember this, okay? Heat and temperature are not the same. Heat is a form of energy. Temperature is a measure of how concentrated that energy is in an object. Heat tells us about the total energy in an object. Temperature tells us about the kinetic energy of the individual particles in that object. So heat here tells us about the total energy, and temperature tells us about the kinetic energy of the individual particles in that object. Now, an example to show this would be a bath of cool water. So you have a bathtub. Hopefully this looks like a bathtub here, right? And your water in here is 27 degrees Celsius. So it's a warm bath. This is almost like room temperature. Okay. Now the water in this bathtub, the mass of this water is more than the mass of the water in a mug. Okay. So a mug with boiling water. So the temperature in this mug here of the boiling water would be 100 degrees Celsius, because water boils at 100 degrees Celsius, and you would have your steam coming out of there. Now what we are seeing is that the heat is much less in the mug than the cool bath. There are fewer molecules in the mug. If I were to take this small mug of boiling water and throw it into this bathtub here, the water temperature would not change very much. But if I were to take this tub of water and somehow throw it into this cup, the contents of the mug will become cooler. So the cool water has a lot more heat energy and a lower temperature than the mug of boiling water, okay, because of its mass. So the mass or the amount of the substance is very important too when determining heat and thermal energy. Temperature can tell us which way the thermal energy is being transferred. When thermal energy is transferred to an object, its temperature increases. When thermal energy is transferred away from an object, its temperature decreases. Okay? So the temperature of the system or the body or the object or the surroundings is important to know so that we can tell which way the thermal energy is going to be transferred, because we said earlier that heat energy, thermal energy, moves from areas that are higher in temperature to areas that are lower in temperature. So now let's look at some real-life examples on page 2. So example 1. If you leave a hot drink on the table and wait for a while, does the drink heat up or cool off? Sounds like a trick question, right? You could probably give your friends this question and see what they come up with. So here we have a table. This is my table. And I have a mug on the table. And my mug has a hot drink in it. So here is hot. Okay. Now, if here is hot, my surroundings would be colder. So let's pretend this is a mug. And my mug is hot at 80 degrees Celsius. And my surroundings, which is the air, okay, so the air in my surroundings is at 28 degrees Celsius, which is normal room temperature for our climate. What do you think will happen? In what direction would the heat flow? Well, we know that it would move from the hotter object to the area of lower temperature. So it will move out into the air in the surroundings, or if the table is colder, it will move to the table. So heat is transferred out of the cup or the mug. Now, if heat is leaving or is removed from the hot object, then the drink inside your cup would cool off. Okay? Now, example 2. If we leave a cold drink instead on the table and wait for a while, what will happen? So here I have my table again and my mug. Don't laugh at my drawing. Okay, and this is a cold drink, and this cold drink is at 10 degrees Celsius, and I have the same surroundings. The air in my surroundings is at 28 degrees Celsius. What will happen to the drink in the mug? Will it heat up or will it cool off? Well, heat would move from the hotter air into the colder mug. If the table is 28 degrees as well, the heat would move into the cup, which will heat up my drink. Let's look at the example 3. You are holding an ice cream cone in room temperature air. So my room temperature air here is going to be 25 degrees Celsius. Okay. How does heat flow between the ice cream, your hand, and the air? Now, normal body temperature is 37 degrees Celsius. Okay. Anything higher than 37 degrees Celsius, it means you have a fever. Now, what is the temperature of the ice cream? Well, the ice cream would be 0 degrees Celsius. It's cold. Okay, it's frozen. And it's mostly made up of frozen water with some flavoring and some milk in there, right? So, which way would our heat flow? Our heat would move from the area of higher temperature, which is my hand, into the ice cream, from the cone to the ice cream, okay? And the hot air in the room will move to the ice cream. Heat will also leave your hand and go into the air because my hand is hotter than the temperature in the room. So we have hand and we have the ice cream. We have the hand again and the air, and we have the air to the ice cream. Alright, I'm just putting this in some colors for you. So the heat moved from the hand to the ice cream, from the hand to the air, and air to the ice cream. So be sure to pause the video and take down all these extra notes, okay? Now example 4. Water is boiled on the stove in a teapot. How does heat flow in this picture? Well, we have a flame here, and this flame is at 1000 degrees Celsius. I have my water here, which is boiling 100 degrees Celsius because water boils at 100 degrees Celsius. The air in my room is 25 degrees Celsius. How does heat flow? Well, it will move from the areas that are hotter to areas that are lower in temperature. It will move from the flame to the pot, and then the heat of the pot to the air in the room. The temperature of the pot and the water inside is higher than the air in the room. Now, if steam decides to leave through that opening there, this is another way that heat would leave. Okay, so heat are going to leave through all these pathways here. Heat is not going to flow from the air into the pot because the air in the room is of a lower temperature than the pot, okay, and the water in the pot. And we also have the heat from the flame moving to the air as well. Now let's write down the scenarios that is happening here. We have heat flowing from the flame to the air, from the flame to the pot, then the pot to the water, and then to the air. We have the, right, so that's this one here, right, so from the water to the air through this opening here, and then we have from the pot to the air, and we have from the water to the air. Okay, so this one here is a complete pathway from the flame to the pot. The pot will heat up, the water will heat up inside, and then the pot will give off heat to the air, or it will give off, the water itself will give off heat through the opening here as steam. Okay, and these are all your heat flows. Okay, so on each of these arrows write the word heat. Now let's look at example 5. You are holding two ice cream cones together. They are both at exactly 0 degrees Celsius. Does any thermal energy flow between the two ice cream scoops? So here I have my 0 degrees Celsius ice cream and my 0 degrees Celsius ice cream. So because there are no temperature difference between the two ice creams, there will be no thermal energy flow. So what's important here to note is that for heat to flow, there must be a temperature difference. Okay, there must be a temperature difference for heat to flow. So there's no flow of heat between the two ice cream cones. Now let's turn the page and take a look at example 6 and 7. A hot cup of chocolate is in your hands and you really want to drink it now, but it's too hot. How might you cool it without using ice or a refrigerator? So my first scenario that I remember doing is having a container with water. And this could be cold water or room temperature water. But the water must be at a lower temperature than the mug or the cup of hot chocolate tea. Okay, so this is my cup in my water. So our first scenario is to put mug or cup in water bath. So we make a little bath for the hot cup of tea. And which way would the heat flow? Well, the heat would flow from the hot tea to the mug to the water. We also have heat flowing from the hot tea to the air. Okay, so it goes to the air, or it goes into the water. So our heat flow here is from the tea to the mug or the cup and into the water. But we don't want this part because we want it to cool faster. So the faster way is to put the mug in a water bath. The second way to cool down hot tea is by using 2 cups. My original cup here with my hot tea, and I have an empty cup here. And what I will do is pour the tea into this cup and then pour it back into this cup, back and forth. Back and forth, we're going to pour the tea back and forth between these 2 cups. So this one here is pour tea back and forth between the 2 mugs or 2 cups, okay? And what would this do? Why would we want to do that? Transfer this heat back and forth. Well, we would want to increase the loss of heat from tea to air. Okay, so why we do this is to increase the loss of heat from our tea to the air. Alright, so these are 2 scenarios that we could use to cool your tea. And at CXC level physics or integrated science, these are the types of questions they would bring to make you think about real life situations where you can apply what you know about the transfer of heat. Now question 7. On a hot summer day, would you feel cooler if you stood under a ceiling fan, and why? So I have my ceiling here and my ceiling fan. Okay, so this is my ceiling fan with all its blades. And here's me standing under the fan. And it's a hot day. So the day itself is hot. Let's say the air in the room is at 30 degrees Celsius. So it's a hot summer day, right? 30 degrees Celsius. Would you feel cooler if you stood under the ceiling fan? And why? Now, fans, even if it was one of these standing fans, so let me try to draw a standing fan here for you, and you are standing in front of it. What fans do, they don't magically cool something. What they do is move air, and this movement of the air increases the rate of transfer between the object that they are blowing on and the air that they are blowing. So this fan here, what it does is pull this hot air onto you, but it also blows that heat from you away. So if you are sweating, it would increase the rate of evaporation of your sweat from your skin and you feel cooler. Okay, so those extra notes that popped up on your screen there, you need to take them down. Okay, write it on this paper somewhere because it's very important, and you will have questions popping up in your assignments or in future in your NCSE exam or any other end of term exam. Alright, asking you to explain these scenarios. So fans do not magically cool something. All they do is move air and increase the rate of transfer between the object they are blowing on and the air they are blowing. And it also increases the rate of evaporation of sweat from your skin and you feel cooler. So in this scenario, if the air is cool, so it's pulling cool air, which is maybe 22 degrees Celsius, and I am feeling warm at 37 degrees Celsius, the fan will pull the cool air, blow that cool air on you, and your heat will flow away from you. And your sweat will evaporate and move away into the atmosphere. So this is what fans do. So now let's look at some temperature scales. And the instrument we use to measure temperature is called a thermometer. Now there are different types of thermometers, and they each have their own application and special places where they are used. So I'm going to label these thermometers, and we will talk about what type of thermometers they are and briefly chat about how they operate. Now at this level, you're not expected to learn off the names of these thermometers or how they operate in detail. But later on, in Form 4, we will need to focus on a few of these thermometers and look at them in detail and know how to use them. So thermometers 1 and 7 are what we call liquid in glass thermometers. This is where the liquid expands or shrinks with temperature change. Thermometer number 4 is something called a manometric thermometer, and this determines temperature based on changes in gas or liquid. Thermometers 2 and 8 are called gas thermometers, and these are filled with gas, which expand or shrinks depending on the temperature. Thermometer 9 is a bimetallic thermometer, and this works with two metal strips. So bimetallic thermometers is something that we will focus on in greater detail in Form 4. Thermometers 6 and 10 are infrared thermometers, and these measure the thermal radiation of a body or object. Thermometers 3 and 5 are digital thermometers, and number 5 especially is a clinical thermometer. So again, in Form 4 we will go into detail about clinical thermometers, bimetallic thermometers, and liquid and glass thermometers. Okay, so these are the types of thermometers and a brief description of how they work, how they measure this temperature. Now on page 4 we will look at the units of temperature and converting from one unit to a next. There are 3 units of temperature. However, throughout this subject as well as in physics later on, we will only be using degrees Celsius and degree Kelvin. Degree Fahrenheit would not be used, but it's still good to know because some thermometers that you find being sold in our pharmacies here do carry a reading of Fahrenheit. So these here are your symbols for degree Celsius and degree Kelvin, or sometimes just kelvins. We also need to know how to convert from degree Celsius to Kelvin and back. Now, in Form 1, you would have learned about SI quantities and SI units. The SI unit of temperature, which is one of the base quantities, is the base unit Kelvin. Okay. Now let's look at how we convert from degrees Celsius to Kelvin and from Kelvin to degrees Celsius. So here we have 2 thermometers. One here is on one side of the thermometer. We have a scale, and this scale is in kelvins. We could see that it starts at 0 at the bottom, something called absolute 0. Here we have the freezing point of water in kelvins, and here we have the boiling point of water in kelvins. On the other side of the same thermometer, we have a degree Celsius scale. Now, this type of thermometer is a liquid in glass. So here we have a liquid in glass that we could see, and as the temperature increases, the liquid will expand, the temperature will go up, the liquid will move up tube. As it gets colder, the liquid would shrink and the liquid will move down the tube. Okay, so this is how this works. Now here you see absolute 0 for the degrees Celsius scale is minus 273 degrees. The freezing point of water here is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. Now these temperatures here are important to know, these two especially. Now the next thermometer here has degrees Fahrenheit on one side, which we don't need to really know, and on the other side is degrees Celsius again. So when you are choosing a thermometer, be sure that you know if it's measuring in Fahrenheit or degrees Celsius. You would rarely find a thermometer being sold locally in kelvins. You would find it in Fahrenheit or degrees Celsius. Now temperatures that are much colder than the freezing point of water can exist. On the Kelvin scale, we call the equivalent temperature of 0 degrees Celsius or minus 273 degrees Celsius. So here, that's on the scale, right? So it's 0 kelvins or minus 273 degrees Celsius. The divisions on the two scales are equal. Okay, now if you look at the markings, it's exactly 273.15 and exactly 0 degrees at the same mark on the same thermometer. So 1 Kelvin is equal to 1 degree Celsius. To convert from a Celsius temperature to a Kelvin temperature, we add 273 degrees to the Celsius temperature. 0 degrees Celsius, if we add 273 to it, we will get the temperature of kelvins, which is the same thing, 273. Now we are seeing 273.15 here, but throughout the syllabus, we are to use just 273. To convert from a Kelvin temperature to a Celsius temperature, we subtract 273 degrees. So let's look here. Let's take absolute 0 kelvins. To turn this into degrees Celsius, we are to subtract 273 and we will get minus 273 degrees Celsius. You should be familiar with working with positive numbers and negative numbers from Form 1 Maths when you did directed numbers. So that's a topic you need to go to revise in math. Revise directed numbers. Okay? And this will help you understand we need to use this negative symbol in front of the number here. And we can have negative temperatures. Now let's convert some of these temperatures here into Kelvin and from Kelvin into degrees Celsius. To change 50 degrees Celsius to kelvins, we add 273. And this will give me 323. Now I don't need to write kelvins here again because our table has the units up here. Okay? Students make the mistake of writing that Kelvin, the units back in the table. We don't need to and you shouldn't. Okay? The units should be in your headings here of your table. Now to change this Kelvin into degrees Celsius, we would take that value of degrees Celsius and subtract 273. And this will give me 192 degrees Celsius. Now in this case here, we have 35 kelvins and we want to subtract 273. So with the directed numbers, we subtract as normal. So that means 273 minus 35 will give me 238. And we keep the sign of the larger number. Okay, so 35 minus 273 is equal to 238. Now we are changing 95 degrees to kelvins, and to do that the rule says to add 273, and here we will get 368 kelvins. Now after you pause your videos and take down all your notes and you revise, you could practice converting temperatures to and from kelvins in lesson 1, activity 1. There's also some other questions based on what we learned from the start of this lesson there for you in that activity as well. So when you finish that activity, come back and we will look at some information that you would have learned in your lesson for states of matter, and we will look at some simulations and scenarios and some graphs for changes between states of matter.